Today we're going to learn about scientific notation and SI prefixes. While this might take you a minute or two to learn, it will end up saving you time in the end. So first off, every measurement needs a number and a unit. You may think it's not a big deal to include units, but it is significant. For instance, in 1999, NASA lost a $125 million Mars orbiter simply because one engineering team used the English system and one used the metric system. Whoopsie. So you always have to have both or it's wrong. Now some numbers are tiny and some numbers are huge. So in order to help make it so we don't write like 700 zeros, we represent it in scientific notation. It just makes it easier on us. If you really want something cool to look at to really grasp how big we are or how small we are, go look at this URL right here, scaleoftheuniverse.com. There's also a couple YouTube videos that will just basically move the slider bar for you. But basically, whenever I've gone to this website, I zoom in and then I'm like, wow, everything's so tiny. Look at all this small stuff. And then I zoom back out and then I feel insignificant. It really gives you a perspective on just scale and how much stuff changes as you go from powers of 10. So take a look at that video. But with this video here, we are going to teach you how to convert everything to scientific notation and use metric prefixes such as centi and milli and killi. So the first rule of scientific exponential notation is that we are trying to express the number as the power of 10, and we want that coefficient that is before the power of 10 to have a number that is between 1 and 10 or between -10 and -1. So another way of saying this is you have to place one digit in front of the decimal, and you can only have one digit. If you have two digits, it's not correct. And then you use a power of 10 as a multiplier. So positive exponents are really big numbers, negative exponents are really small numbers. Both of them the coefficient can be positive or negative. That doesn't change the size of the number. And then zero exponents, such as 10 to the 0, is another way of saying 1. So let's do a whole bunch of practice today. So what you see right here is if we have 808,972, that is in what is called decimal notation, mainly because it doesn't have a power of 10 next to it. So in order to convert it to scientific notation, what I do is I start at the decimal, which is not shown, but it is located to the right of the 2, and I count. So meaning 1, 2, 3, I move it over. I want to move the decimal over 3 locations, and that's what gives me my coefficient, that of 8.972. Then my exponent is how many did I move it over. If I move it over 3 to the left, that's a positive 3. So for the next number, we have 12. So how would we express 12 in scientific notation? So you start at the decimal, which would be to the right of the 2, and you move it 1 over to the left. Therefore, this number is 1.2 times 10 to the first. For the next number, it is 0.000159, or another way of saying this is in order to move that decimal, you're going to move it to the right 1, 2, 3, 4 places in order to put it just to the right of the 1. So that is 1.59 times 10 to the minus 4. It's negative because we moved the decimal to the right instead of the left. For the next one, we moved it over 3, so 8.0 times 10 to the negative 3. And for this one, look at all those zeros, so that is 7.1 times 10 to the 6th. We moved it left, so therefore it's going to be positive exponent. Alright, so try the other direction. So all the rules are going to be backwards. This time you're going to convert from scientific notation to decimal notation. So for this first one, 7.63 times 10 to the negative 5, that means you're going to take that decimal and you're going to move it left 5 places. 1, 2, 3, 4, 5, and it's going to end up being 0.123400763. So that decimal moved 5 to the left. For 8.2 times 10 to the third, that decimal needs to move 3 to the right. 1.1 times 10 to the negative 6, it's negative, so move it to the left. And on this one, I did end up keeping that 0. The 0 at the end shows what's called significant digits. Your textbook just says, we'll look at it later, or look at the appendix. So if you're really interested in knowing a lot more of the technical correct way to represent numbers, go read that. We will look at it a little bit in the lab. For letter D, we have 4.109 times 10 to the 7th, so that number needs to get bigger. Remember, those positive exponents are big numbers, so make that decimal bigger. and you can see it got a lot bigger. And then once for e, once again the exponent's small, it's negative, so 10 to the negative 2 means this 3.1 number should get smaller, and it does. So I hope you did a good job practicing those. And then we can move into our prefixes. So this is the table in the book that tells you all about the different prefixes. The ones in color are the ones that are most common. So those are the ones I would really focus on getting to know well. Now let's practice turning these decimal notations into scientific notation and then allowing a prefix to be introduced. So we've already practiced turning decimals into scientific, so you should be able to convert each of these, and go ahead and do that on a piece of paper. Turn each of these into scientific notation. And then we will work together to turn the scientific notation into a prefix. So for this one, it becomes 2.9 times 10 to the minus 3. Now if we look on our chart on the previous page, 10 to the minus 3 is the same thing here as saying milli. So we can just directly substitute in milli for 10 to the minus 3, and milli is represented by a lowercase m. So this becomes 2.9 milligrams, and instead of writing 10 to the minus 3, you just write milli. For this next one, 8.27 times 10 to the third. 10 to the third can be substituted with the prefix killi to become 8.27 kilograms. For this next one, it is 1.1 times 10 to the minus 2 meters. 10 to the minus 2 is centi, so we replace that with centi to become centimeters. For this one, it is 3.5 times 10 to the minus 5 grams. Now notice there was nothing on the chart. So sometimes your book will ask you to do things such as change that negative 5, represent it not in like correct scientific notation form, because notice that 35, there are 2 digits, and you're not supposed to have 2 digits on the other side of the decimal. You're only supposed to have 1. But in doing it this way, you're able to represent it with a prefix, because now you can substitute in 10 to the minus 6 for micro, and it becomes 35 micrograms. You could have also gone the other way, where you went to 10 to the minus 3 and represented it as milligrams, and it just would have been, what, 0.035 milligrams, and so that's another way of doing it. So with this last one, it's a big number, small number, lots of zeros though, so that becomes 7 times 10 to the minus 9, which is the same thing as saying nanometers. Alright, so now it's going the opposite way. So now just replace each of the prefixes here with the power of 10. Feel free to stop the video and then check your work. So 8.9 times 10 to the minus 3 is milli, killi is 10 to the third, centi is 10 to the minus 2, and micro is 10 to the negative 6. Alright, now we're going to switch over to unit conversions. So this is a method that we're going to use so often in chemistry calculations. Basically relies on the idea that every conversion factor, which is what you see down here, these are considered conversion factors. They are equal to 1, and the reason for that is the numerator, the part on top of the fraction, is equivalent to the denominator, which is the part on the bottom of the fraction. So in this conversion factor, 1 pound is equal to 554 grams. That being said, that's why it doesn't matter which one you write on top. You can either write it as 1 pound over 454 grams, or you can swap it up. How you decide which one you need is you're trying to get what's called your units to cancel, and we will see that illustrated in this next example. So in figure 1.4 in the textbook, astronaut Harrison Schmitt is said to weigh 180 pounds on Earth, and his moon suit is said to weigh the same amount. So it's assumed that his mass in pounds is 180. So this question is simply asking us to take those 180 pounds and convert that into grams. Then the extra question says, what would be his mass in kilograms? So once we get it in grams, it's asking us to convert it from grams to kilograms. So we're not doing anything with Earth versus the moon, conversions like that. It's just Earth. We're just looking at Earth. So the first thing you want to do is you want to write down the information from the problem. So in this case, we have 180 pounds. Now we need to convert that in the first step into grams. So we have two options. We can either use this conversion factor, which has pounds on top, or this conversion factor, which has pounds on the bottom. What you want to do is you want the unit that you're trying to get rid of, which in this case is pounds, to be on the bottom. And the unit you're trying to get it into, which in this case is grams, needs to be on top. So that's why we're going to use this conversion factor. So in this case, your pounds end up canceling out, leaving you with grams on the top. So now when you have your answer, the units are in grams. It's the same thing as if you have 5 divided by 5. The 5 is on top and bottom, so they're canceling. So in this case, the pounds canceled because it was on top and also on bottom. So now we've answered the question of how many grams his suit weighs. But what about kilograms? So I go to the next line and I write down the number. But now it's in grams and I need to convert it to kilograms. So look at these conversion factors down here. Here are our options. 1,000 grams is equal to 1 kilogram, so that's our conversion factor. Now we want to cancel the grams and we want to be left with kilograms. So that means grams should be on bottom and kilograms should be on top, which is what we see in this conversion factor. So that's my conversion factor. And I guess I should also have said that whenever you do it like this, 180 times 454 divided by 1, that's what you would type into your calculator. And I hit enter after every step just to make sure I'm doing it right. So in this case, 81,720 times 1, enter, divided by 1,000, enter, and that will give us our final answer of 81.72 kilograms. So this is a systematic way of answering questions. Sure, you could have done this math some other way, but I think that you'll be happy later on in this course if you get in a habit of using conversion factors. So many chemistry problems can be mastered simply by learning how to use the conversion factors and letting the units tell you how you're dividing and multiplying. Let's do another example. This one's not in the chemistry world, but it's in life. Eggs. Let's say somebody asks you, how many dozen eggs do you have? And you say, I don't know, I've got 90. How would I convert from 90 eggs to a dozen eggs? Well, the first thing you'd want to do is make a conversion factor. So if I were to ask you, how many eggs are in a dozen eggs? You would tell me 12. So the first thing you want to do is make a conversion factor. So you could say either 12 eggs is equal to 1 dozen or 1 dozen over 12 eggs. It's the same thing. So now I need to figure out how can I use those conversion factors to create an answer, and I need to not forget my units. So I write down 90 eggs. That's what I'm starting with. So now which conversion factor do I use, the first or the second? I hope you said the second, and that's because the eggs are on bottom and we're left with dozen, which is what we're trying to attain. So in this problem, the eggs will cancel out. So then I solve it. I just simply typed in 90 times 1, enter, divided by 12, or you could have said 90 divided by 12 gives me 7.5 eggs. And so this is the basis behind what is a conversion factor. Now go read section 1.8.